All right, this is a video on curve sketching and some extra examples that we had, and we're going to start off with number 3, just looking at the ones we got done in class versus the ones we didn't. So the function we're trying to graph here is y equals 2x to the 5/3 minus 5x to the 4/3, and I don't remember if we did this one in class or not, but I don't remember doing it, so we're going to go ahead and do it on the video. And we were supposed to identify all the intercepts, the relative extremas, the points of inflection, and the asymptotes, and use this information along with any sign diagrams that we create to then graph or sketch the graph. So the first thing I usually try to do is to find my x and y intercepts. To find the x-intercepts, you're going to plug in 0 for y. So this would be 0 equals 2x to the 5/3 minus 5x to the 4/3. Now, since they both have x to the 4/3 in common, we can pull that out as a common factor. That would leave me with 2, and then this would be x to the 1/3 minus 5. We would set each of those parts equal to 0. This first one will just give you x equals 0. The second one, though, you would add 5 and then divide by 2. And then you have to raise everything to the 3rd power because it's a cubed root. So it's actually 125 over 8. So I have x-intercepts of 0, 0, and then 125 over 8, comma 0, which will turn that into a decimal when we actually go to graph it. Okay, and then for the y-intercept, you just plug in 0 for all the x's into the original function. So 2 times 0 to the 5/3 minus 5 times 0 to the 4/3. Since everything's times 0, it's just going to be 0. Okay, so now we want to talk about the extremas, the maximums and minimums, the relative max and min. Remember, to find that, we need to take the first derivative of our original function. So here was our function. The first derivative of this would be y prime is, let's see, 5/3 times 2 would be 10/3. We subtract a 3 over 3 since we subtract 1, so that would now be 2/3. Minus 5 times 4 is negative 20 over 3. And then we subtract 3 over 3 again for 1. That would be 1/3. Okay, then we want to set this equal to 0 to find our critical values. Remember, those are the numbers that could possibly be relative maxes and mins. I think I can pull out a 10/3, and I can also pull out an x to the 1/3. That would leave me with just x to the 1/3 for the first one because it has to add back to 2/3 minus 2 because you pulled the 10 out and the 3 out, but you'd still have a 2 from the 20. So we set those equal to 0 to find our possible critical values. This one will just be 0 since it's times the x. This one, though, we'll have to add the 2 over. And then we'll take this by cubing both sides. And the possibility is 8. So then remember, our next step with this is to place this information into a sign chart to figure out if we're increasing or decreasing on those regions. So this is 0, 8. So that's negative infinity to 0, 0 to 8, and 8 to infinity. Test value in each region, negative 1, 2, and 10. You plug them into the first derivative, remember the actual derivative. So this would be 2 times negative 1 to the 5/3 minus 5 times negative 1 to the 4/3. You'll probably want to use your calculator, but cubed root of negative 1 is negative 1. Raise it to the 5th power, it's still going to be negative 1. So this ends up being negative 2. Cubed root of negative 1 is negative 1, but you raise it to the 4th power, it'll become positive, but then you multiply it by the negative 5. So it's going to end up being negative 7. So this region is decreasing. If we plug in 2, since 2 is not a perfect cubed root, we'll probably want to use our calculator here. So 2 times 2 raised to the 5/3 power. Oops, it didn't give me a base there. Hang on. 2 times 2 to the 5/3 power. There we go. And then minus 5 times 2 to the 4/3 power. Getting negative 6 point, negative 6 point something. Was it negative 6.25? Yeah. So that makes that negative, which is decreasing. Let me double check the first one again. I might have made an error on that one. So let's see. 2 times parentheses negative 1 to the 5/3. And then we're going to minus from that 5 times negative, 1 to the 4/3. That one's not coming out quite what we had before, so I don't think this calculator is doing what I need it to do, so hang on. Let me get my scientific calculator for real. I just figured out what I did. All right, I had to look at it for a second. I was plugging into the original function. See, not paying attention. You are supposed to be plugging into the derivative, and I even told you to do that. So let's redo this. So negative 1 needs to go into the derivative. I was looking at the line above it. So this is 10/3 times negative 1 to the 2/3 minus 20/3 times negative 1 to the 1/3. So that's going to be negative 1, cubed root is negative 1, square it's positive, so this will just be 10/3. Negative 1 cubed root is negative, times another negative out front will be positive, so this is 20/3, this is 30/3, which is 10. So this region is actually positive, which means it's increasing. Okay, now we're on the right track. So then we need to do 10/3 times 2 to the 2/3 minus 20/3 times 2 to the 1/3. So this time we'll get our calculator back out. And this is 10 divided by 3 times 2 to the 2 divided by 3 power. And that is 5.29 minus 20 divided by 3, which probably needs to be in a parentheses. Let me back up. You have to be really careful with these calculators on the computer. They don't always do the order of operations the way you think they would do it. So just extra parentheses are always helpful. Okay, that's that. And then minus 20 divided by 3 as a fraction times 2 to the 1/3. Okay, and this comes out to negative 3.1, so this is a negative region, which means it is decreasing. And then for the last one, 10/3 times 10 to the 2/3 minus 20/3 times 10 to the 1/3. So 10 divided by 3 times 10 to the 2/3, and then minus 20 divided by 3 times 10 to the 1/3. Okay, so this comes out as positive, and that means it is increasing. Okay, so what we know so far is that if we're increasing, remember, to decreasing, that means we have a relative max. As long as they were defined at this point, there's no reason we can't plug 0 into the original function, so we are defined there. And then this is decreasing to increasing, so that means this is a relative min, and we want to find those point values. So we have a relative max and a relative min, and we need to figure out those ordered pairs. Ooh, my screen just went black. Hang on just a second. Okay, so to figure out the ordered pairs, remember we plug them into the original part. So this, we plug in 0 into the original function, which was right here. So that is 2 times 0 to the 5/3 minus 5 times 0 to the 4/3. That's just going to be 0. So our relative max is at 0, 0. And then if we plug in 8 into the function, that is 2 times 8 to the 5/3 minus 5 times 8 to the 4/3. This is cubed root of 8, which is 2 raised to the 5th power, which is 32 times 2. So this first term is 64. And then cubed root of 8 is 2 raised to the 4th power is 16. And then times 5 is going to be, I believe, negative 80. Yes. So that is negative 16 overall. So I know I worked through that pretty quick, but you would use your calculator for that. So that's the 0.8, negative 16. So let's go back up to our chart and fill that in. So 0, 0 is the relative max, and 8, negative 16 is the relative minimum. We need the points of inflection. There's not going to be any asymptotes. I'm going to go ahead and write that. The reason for that is that asymptotes only occur if you have something undefined in your denominator and your original function did not have a denominator. So usually those only occur with rational functions. So points of inflection have to do with, remember, concavity. So we need to do are we concave up or concave down? So we need to take our second derivative. So let's look at what the first derivative was. Here it was. So this is first derivative. So y double prime would be 10/3 times 2/3. So that's 20 over 9. X to the subtract 3 over 3. So that'd be negative 1/3. And then we have 20 over 3 times 1/3. So that's going to be negative 20 over 9. And then subtract, and we'll get x to the negative 2/3. So when we go to factor this one out, this is a little bit harder. We need to pull out the 20 over 9, obviously, and then they have, whichever one of them is the smaller exponent is the one they have in common. So it's actually the negative 2/3, because that is a smaller number on the number line. So when you pull this out, you have to be careful. This is negative 1, take away negative 2. So it's actually adding 2 back to it. So it's going to be x to the 1/3. And then this would just be minus 1. So this first one is going to be 20 over 9 x to the 2/3 equals 0. That's going to be when x equals 0, because that's when it's undefined. And then at x to the 1/3 minus 1 equals 0, that's going to be equal to 1, and then we cube it to get the third to go away. So it's just 1. So then remember, we do a chart for concavity. This is 0 and 1. So negative infinity to 0, 0 to 1, and 1 to infinity. Test values would be negative 1, 0.5, and 2. We plug those into our second derivative. Now I'm running out of space here, so I already worked this out. I got negative, and then negative, and then I got positive by plugging these numbers into that second derivative. What that means is that we're concave down, and then down again, and then up. A point of inflection only occurs when you change from down to up or up to down. So the only point of inflection is 1. So point of inflection happens at 1, and we need to figure that out by plugging it into the original function. So 2 times 1 to the 5/3 minus 5 times 1 to the 4/3. I believe we got negative 3 for this. Yes. So that's going to be my point of inflection. The other one is a max or min, because remember, if it's not a point of inflection, that meant it was already a relative max or min. So this is, let's erase that guy. Sorry, my page is jumping all around. So let's go and graph that. It flipped up. So my point for inflection was 1, negative 3. And then I'm going to plot all this information just kind of right here, because that way we can read what we have. So I'm going to need some marks on my graph. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Probably need my lower part to go a little bit longer. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so 0, 0 is going to be, I'm going to do everything in red, is going to be a point on our x-intercepts. 125 divided by 8 is also an x-intercept. So that is 15.625. So I think this was 16. So about 15.625. 0, 0 is also a max. 8, negative 16. So 1, 2, 3, 4, 5, 6, 7, 8. And then I went all the way down to 16. That was my relative minimum. My point of inflection was at 1, negative 3. Remember, that's where I changed from my concavity. And remember from our information, if you looked at your critical values, which remember were our maxes and mins, it tells you when you're increasing or decreasing, and it's hard to scroll through this. But we were increasing and then decreasing and then increasing between our maxes and mins. So on this side of this, because this was a max, this was a min, on this side we're increasing. That means we're coming up towards the red point. On this side we're decreasing, so we're going down towards the second minimum, and then we're increasing again. So you can see that kind of makes sense. And from the point of inflection over, this is all concave down, and the other point of inflection part over, it's all concave up, which is also what we did discover. So this was down, down, and then up. So that is it for this one, and hopefully this gives you another example. I'm going to have to cut the video off here, and I'll do a second part for the two other graphs I wanted to show you.